this session, and we are very happy with Gustav and Stefan to share this moment with you. We have a heavy agenda, so I will be quick. It's not usual that one of the session chair actually makes a talk before the presentation, that we need to introduce the topic. So first important point is the fact that actually our friend and colleague Luca is actually has his birthday since 2 days, and it's very important that we actually thank him for his outstanding commitment and for his effort throughout the years. He turns 65. So you can see that he's in a great shape and still have promising future works, his workshops. So happy birthday!
Thank you very much.
I'm very proud of having been part of this project. Probably some of you remember 3 years ago we came with Gustav actually talking about this project, and many of our colleagues joined us and trust us. So now it's actually published, and you can see that it is there on the desk, screen the desk at our conference. Unfortunately, one of our co-authors, Gilles and Franz, passed away a few days ago, just 3 days before he received the paper copy of the book. Actually, Wrzaczek was a specialist in environmental economy. So, please, go ahead. Okay, now the question that we are interested in is whether nonlinear feedback strategy, the Nash strategy, really exists. Let me explain. Some of you are not familiar with this concept. It's a very actually simple derivation process, and I want you to see how it works. I will proceed in the Camille and Schwartz fashion, if you allow me to do it. I mean, I have not much technicality in this case. So it's a common group accumulation game, which is very common, initiated by Feichtinger and Luca, that Franz knows very well. Actually, it's a simple problem over a finite time horizon with 2 players, which are symmetric, and they actually control effort, which is to accumulate the common good or service, as you can see. So J is this state variable which depreciates over time, and then you see we have a linear quadratic utility function for each of the players and the cost function. So it's a very simple structure, as you can see, with limited number of parameters. And for this simple game, we know the cooperative steady state solution, which is given here. We also are able to derive open Nash equivalent steady state. And what we would like to do is to compare how we derive actually the linear feedback strategy and the nonlinear feedback strategy. And the difference actually is very interesting. So we still continue with symmetric players, and we use the Berman principle in this perspective. And then you see we have linear feedback here and nonlinear feedback here. In this context, you know this how it works here. You need to make a conjecture to deriving the necessary condition and plugging it in the Berman equation. Then you make your conjecture, you plug, and you resolve the system of algebraic equations, which is actually straightforward, as you know. For the nonlinear feedback, you actually proceed in a different way. We are interested in eliminating the derivative of the value function with respect to the state variable. So you see here we plug the control variable as a function of the state, as you can see. But still remains here the value function. So no guess, no conjecture. That makes, that's very interesting to proceed in this way. So that's Tutsi and Mignot procedure in 1990 in Journal of Economic Theory. And the paper, by the way, is very difficult to read. and other authors, Doppler and Long, Wirl and others, actually make it more understandable for common people. So you see, you get this, sorry, when you differentiate this with respect to J on both sides, then you get this equation, which is the nonlinear feedback rule. But then you have this, I skip the limiting conditions, and this is also what you get for the steady state. And finally, for the linear feedback, you get this result at the steady state for the state variable. And for the nonlinear, you just need to have actually to plug the value of u into the nonlinear rule, and then you get actually this written as this, which actually results in this. And we can show that we have this ranking, which means that the nonlinear feedback is very close to the cooperative solution, and much better than the others. I mean, the opposite than the linear feedback strategy. And then this is, of course, very interesting. So this is a representation. You can see this is the linear and the nonlinear feedback. So you see, you get this here, the steady state here, which is greater than the one here. Anyway. So here, what we have actually, we show that with this procedure, actually, we provide to these nonlinear rules a Pareto superiority over open loop, which was not the case with linear feedback solutions in most of them. Then we preserve the spirit of the Sapien perfectness property, which is so much important for game theories. But we have drawbacks, and the first drawback is symmetry property, and Franz will talk about this. We have also the fact that we have a scalar state. One dimension is not enough to represent many important realistic problems. The third case is when you have a number of separable additive controls. It works with one control most of the time. And then restriction on the set of the state space, which has been emphasized by authors like Ogun, Casimo, and others. Now the question is, in 2024, in last October, if I remember well, Pierre Bernard, which cannot be here today, actually questioned the validity, the mathematical validity of these strategies with a proof showing that it's not a Nash equilibrium. Why? Because it's not the time horizon is actually not clearly defined. We don't know when the game stops. Actually, so this is not. He said it's not. It cannot be a Nash equilibrium in this situation. And this critique comes very late, 34 years after the paper by Tutsui, and it makes it actually very destructive in the sense that many of our colleagues invested effort and published papers in the area since many years, and we have important results. And then there is a support, considerable support for this strategy over the community. Now, I have some citations by Pierre Bernard, which actually correspond to some email exchange. Now he said we need to make to put things in order in some way. Well, it's a very, tough task to do. But I would like to emphasize something. Not everything is black or white in this situation. I mean, you can see in the paper, interesting paper by Tasnim and co-authors, among which our colleague, which is not here, Asymmetry is involved. They have an experimental study that shows that with players, that almost more than 40% of the players involved in this experience, they actually use nonlinear feedback strategies. And they reach the steady state that is computed according to the rule that I presented previously. So you see, we cannot rule out this strategy on behavioral grounds. So we actually need to fix the problem today, and for this we have actually invited 3 superstar researchers that will actually maybe help us to better understand how we could actually proceed to. I let our friend Gustav introduce the presenters. Thank you.
When Fuhr proposed this session here, I was a little bit skeptical at the beginning, particularly when Pierre Bernard, who was invited by Fuhr and by us, also with some special reduction of the registration field. So refused to attend, and he said he's too old and so on. But then
he's younger than you.
But then we were very happy that we had now 3 prominent and competent speakers here in this field. The first is Luca Lambertini from the University of Bologna. He will start. The second one is my colleague and one of the oldest Franz here in the room, Franz Wirl, who was also professor at the Technical University, later one in Magdeburg and then at the University of Vienna, and he recently retired. And the third one is one of the key figures in bifurcation theory and complex behavior of optimal control systems, Florian Wagner from the University of Amsterdam. And as you can see here on the auditorium, that's probably the most important section, at least with respect to application oriented. Because as you can observe, this workshop has now the tendency that it is split between pure or more or less pure mathematics and application, mostly in economics and operations research. And please, I give the floor to Luca Lambertini.
If it doesn't work, I can just go back to the phase diagram of the original paper in freshman in 87 econometrica to tell the story I have in mind in order to play the role of the devil's advocate in favor of the resilience of the analysis in nonlinear strategies. Straight away. I will anticipate the nature of the problem. The nature of the problem is complexity. Okay? When we talk about a continuum of nonlinear feedback strategies, no matter whether we talk about only the stable ones or the entire continuum, because the residual portion is unstable. Okay, if they do exist, which I think they do. Okay, but the problem about complexity using the same building blocks already emerges in the repeated static supergame very well. Okay, and my point is that the economic sense of that model is very clear, and it's going to be not only this, but anything even vaguely related with the static repeated version, the worst nightmare an antitrust authority can think about. Because basically, if you start saying there is no problem about price adjustment, okay, so forget about the state equation, and suppose that the same elements are composing a basic static game which can be repeated in discrete time in order to analyze cartel stability using any fault theorem. Okay? Of course, firms could locate themselves on the frontier. Bingo.
I tried to start this Zoom call, but you can.
Okay.
Yes, I tried to.
Okay. So the point is, suppose you get that you keep an eye on the repetition of the static game in discrete time. Okay. If they don't jump the bar for full collusion using the empirical strategies for optimal punishment, it doesn't matter. Okay. They can still collude partially in infinitely many ways, less or more intense. Okay? Okay, this is not the paper. But it's not, it is vaguely nonlinear.
You missed nothing.
And then, if you observe the solution of the repeated game, you have also, and this is our fault. Our fault, I mean, industrial economists' fault, because I was born as a young researcher in industrial economics, and not immediately inside the domain of differential games. But when we think of partial collusion, we should think of two facts. That term should coordinate in the continuum. Oh, Nico. Okay, it's almost impossible. So, okay.
Sorry for the
Super. This is possible. No problem. I'll be. The old way.
Yeah.
It doesn't work.
Stefan.
It doesn't work.
Yes.
Okay, suppose you are facing the situation, okay? There is no state equation, there is no state actually, okay? They are permanently on the correct notional decreasing linear dimension function. And then they find out that in order, the data have the side. I was writing the slides while driving, so if there is a type of field, please excuse me. This is obviously something that I should have considered. Okay, so that is the condition on the discount factor, whereby all of them using heuristic strategies in this example can locate permanently on the frontier of monopoly profits. Okay? If this is not the case, they still may collude partially, okay? Possibly very much and very close to the frontier, but not exactly on the frontier. But basically, this means that when they do not locate upon the frontier of illicit profits, they may locate in uncountably many positions below such. This poses a problem of coordination in the continuum for the firms, which should, without communication, choose simultaneously the same amount of collusion. And this also poses an enormous problem to the competition authority. Okay? So it's, say, any repeated game like this immediately poses a problem in terms of complexity in the continuum. Okay? Even worse, if we introduce the notion that there exists a notional demand, but eventually they will locate exactly on the correct notional demand only.
Could you stay here such that Nico could?
Oh, yeah, sure. Okay? So this is something that Jean-Pierre considered embarrassing, very embarrassing, because we know very close to nothing when we stipulate that they may choose the intensity of competition in a continuum. Okay? In a subsection of the available space, which is entirely Pareto efficient for terms as compared to the one-shot Nash equilibrium, the Coulomb Nash equilibrium in this case. Okay? Now,
You just
okay. Okay, now we are back into the problem with the dynamics of the state. Okay? There is a single state and controls one for each term. Okay? I'm not using the wording in Tsutsumi. Okay? Because the initial pages in the paper are totally unreadable. And this is the source of the reaction by Pierre, which is right literally. However, How can you, I would like to go back 2 slides, but
Does it with the remote?
sometimes the roll. Now you. Okay. Sorry about this. Okay, the point is, we would like to check the nature of the solution for linear and non-linear field examples. Okay, so we have a first-order solution which generates a quantity, an optimal quantity. The instantaneous quantity is 0 or p minus c minus s times the partial derivative of the quantity. Okay, which requires the quantity, the partial derivative of the quantity function to satisfy the right condition. So technology today is not friendly, okay, in general, in order for the quantity to be actually positive. Otherwise, the ultimate quantity is 0. Okay? Then we have the possibility of solving the first order condition with respect to the partial derivative. Yes. And then from the equation of the continuum, we can calculate literally any nonlinear strategies plus the cone limiting the relevant region, and the cone is made up by the 2 linear feedback strategies. Okay, imposing this system and so on. Okay, now 2 points. Okay, this is the crude one. Okay, you have the stable linear feedback strategy, the unstable one, and then in the middle in this region, okay, you have a continuum of linear feedback strategies. Some up to the point capital P are stable, all the rest are unstable. Okay, of course, and this is another point raised by Pierre, we should also account for, in analytical, mathematically speaking, and informally, okay, for the remaining sections of the graph, which is populated by infinitely many isomorphs. Okay. However, given the story, say the economic meaning of the model, anything, literally anything of economic interest, which may happen in the field, is in the south region. I have just described, in the sense that if you look at the points, the first one is the steady state generated by the open solution. Then you have the Nash equilibrium of the static game. Capital C is the equilibrium point when the firms solve the differential game in order to collude on the Pareto frontier, that is, on the frontier of industry profits. And then capital M is the profit they would do in the static game repeated. Okay, so the initial step. Okay, anything above this triangle is not our interest. Okay, then yes, then okay. It may not be so clear, but I made you bold the lower end of the relevant linear pieces. Okay, up to this value of p, the optimal feedback output is 0. Okay, this is a graphical reproduction of an argument that appears in Fersman and Kahneman and Tizianen with only in the analytical version. Okay. It's a story, a graphical storytelling of what would be at the end of the feedback solution for the characterization of the linear feedback strategies. They don't speak about the nonlinear ones, okay? So anything below the bold piecewise linear cone with the two flat parts is the border out of which firms will never move because the economic sense of the problem is confined at the bottom of it. Okay? Given that, we should go back to this. Any solution coming back from the first order condition when Q is positive is necessarily a maximum point because the second order condition is nothing else than the first derivative of the first order condition when you see just minus Q. Okay? That is necessarily a maximum point. Okay? If it's a maximum point, any nonlinear strategy is also conducive to the Nash equilibrium. It might be unstable, okay, but there are infinitely many stable ones. Okay? The real problem is, suppose we are the firms. How can we credibly coordinate without written communications or WhatsApp or anything else? Okay? In order to generate anything strictly correct in a continuum of, say, leaving aside the portion of the continuum which is unstable. Okay? It's a classical problem posed by Franz. Okay? So I'm saying, basically, these are Nash equilibria. They also have an economic interpretation, a very sound interpretation, because they are just confined inside the relevant problem, along which you can generate anything of interest for an industrial context. Okay? The second order condition is satisfied, but suppose, for instance, P0 is here. Okay? If P0 is here, it cuts literally time zero, any isotime conducive to a stable equilibrium. But I may do what? Can I say, rely, strictly speaking, on Pareto efficiency? Pareto efficiency is not contained in the notion of Nash equilibrium in general. And this is not a cartel. If it were a cartel, then we could say, as in the static repeated game, go as high as possible because we are coordinating implicitly. Okay? But these are Nash equilibrium, full stop. They may be more or less profitable, but these are not collusive actions. Okay? So Pareto is a problem. And the fact that we cannot communicate may give rise to an infinite number of strategic mistakes. Given any plausible P0, admitting a Q star being positive. Okay? So according to me, the problem is not the existence. The problem is the terrible complexity that it poses to players and, moreover, to observers like us, and sometimes ourselves inside, like me sometimes, inside the competition authority. Okay? Thank you.
Thanks for organizing this session. Second, I thank you also for distributing the Bernard paper, because given my age I get a little bit sloppy about the reading. So, and I hope you forgive me, I'm not fully to the point of the existence of nonlinear feedback strategies, but I try to achieve something. Because the major point is a little bit different, but it is related. Okay, this is the content. I think you can read this, and in order to save time, I jump right away. So then, the motivation is the following. The assumption, as we've seen so far, of symmetric games is very common in differential games. And we all know why it's the case. But of course, this is an unrealistic assumption, not only for Austrians, if you allow me to say so, but I think we agree on, because in few players game, the assumption that two persons have the identical same preferences contradicts the genetic differences we often. Another realistic assumption, in contrast to this unrealistic assumption, is that the strategies are non-negative. I will apply in the following to kind of global warming games, and there may be some hands raised because a lot of people talk about nowadays about negative emissions, but of course there is no such thing like negative emissions. Negative emissions is a different activity where you take the carbon out of the atmosphere, but there's no such thing like negative emissions. So the second assumption I pay tribute is that the strategies must be non-negative. Now, what is the objective of this presentation is what are the potential consequences of asymmetric players' preferences and non-negative actions in economic laws. And the result is that perfectly symmetric games need not provide a generic representation of an asymmetric situation. Yes, there are many asymmetric games where the treatment of the symmetric game is generic, but in the example at least I present, and there are fortunately other examples, it will not be the case. And this is the story I want to tell, and then briefly comment on the nonlinear feedback strategies. The literature is found known, and I think I will quote on this Bernhard's story later. So this is the framework. The framework is the Theoretical Commons. It's the Dr. Long paper. Many follow-up, Wrzaczek, Benteng, and two others, as well as Schumacher, with Werder and others, and Jakob and Wagner have used the same. Given the familiarity with this law, I jump right away to Hamilton equation, and the crucial the crucial difference is that the first player has higher external costs on the stock. Okay? We comment on that. This is the only truth. I simplify to make the point very strong that there's no depreciation, which applies to global warming anyway. So if we apply this assumption and the condition that U must be non-negative, then we will have a stopping point for the first player, because the first player cares more about the global warming, so we will stop in finite time. And this allows us to separate the state space into three domains. First, both limits. Second stage, only the guy caring less about the environment limits. And third, all stop limits. Okay? So this gives, we solve the game from the backward. In the third phase, the value functions are given a net present value of the damage. In the second phase, where player 1 stops and player 2 still emits, the player 2 acts as a monopolist, and the solution of the value functions are then not shown and indicated by R's. And then in the first phase, both players emit, and the Hamilton-Jacobi-Bellman functions after substituting the optical strategies are given. Okay? So look at the result. In the thin line, we have the symmetric equilibrium. If you ignore the control constraints, you get the yellow line for player 2 and the blue line for player 1. So in this, if you ignore the control constraint, the symmetric solution is GDF. It's a good approximation. But so you think now at first that you get this no problem, because now you just hatch for player 1 the interior strategy with the boundary strategy. But this cannot be the equilibrium. Why? Because the moment player 1 surrenders the monopoly position to player 2, player 2 will choose his monopoly position, which is much more conservative, and will be the yellow line. So there's no possibility to patch continuously. Okay? So the equilibrium, and if there's a better suggestion, is that following, that player 1 surrenders rather early or at low stop levels. His emissions, he stops, surrenders, gives a monopole position to player 2, and this is then the equilibrium. So to go a little bit away from this underlying interpretation, the upshot is that the symmetric equilibrium is far off the true asymmetric equilibrium. And moreover, the asymmetric solution will be discontinuous. And how to do it, and it's a little bit, a chart is a little bit overloaded, but the crucial feature is here that I just got the value function. So the blue is the value function for interior. This is for the first player, yellow or orange for the second player. And the green dashed line is the value function of the first player if he stops emitting. And then you see at around, I don't know, 3 or 4, for player 1, it's optimal to give up emitting because of caring more about the problem. So I'm coming now to the asymmetric, to the symmetric case and the extreme. So here I give an extreme example, where again you have the symmetric equilibrium, which is the yellow line. Then you have an asymmetric, you have a nonlinear feedback strategy equilibrium, and then you have again the asymmetric equilibrium, which in this case is an extreme one because player 1 surrenders already at period 0. Now let me briefly comment on this nonlinear feedback strategies. I come back. I recall when I met Engelbert in the early 90s, he came to me and said, "Look, Franz, we have solved the tragedy of the commons." Well, it's just expressive seducism, but of course, nobody solves the tragedy of the commons. I thought from the very beginning that this is somehow nuisance, but in the end, you have to follow the proverb. If you can't beat them, join them. Okay, so I've joined them as now, and now come back to the critique, as I understand it from the analyst, that if you go into this game, while the linear feedback strategy reaches the steady state in infinite time, and recall at this point there is a replacement, there's only value matching, no smooth pasting. The nonlinear strategy will hit the stopping point in finite time, and if it does so, you could argue there must also apply smooth pasting, because it's infinite. So maybe this is the core of Bernhard's critique, because the nonlinear strategies stop in finite time. There should be additional boundary conditions. To cut a long story short, if you, and I will comment on this briefly, if you allow for depreciation of the stock, it will not work. Because this was the original projection a long time ago, that I can kill dogs no longer by applying smooth pasting. So I just give you a brief summary as I understand the boundary conditions and Bernhard's remark. So if you have optimization, then you have actually with reversible stopping, you have value matching, smooth pasting, and supergames. Okay. If you make the stopping irreversible, then you lose the supergames. If you have a dynamic differential gain, symmetric and reversible stopping, you still have value matching and smooth pasting. No? But in my case, delta 0, any stopping must be irreversible. No? So this is different. If you have a differential gain, which is symmetric, and you have irreversible stopping, which means you exit, you lose the smooth pasting condition value matching. No? And this you have in my solution from before. In this case, for example, no? I don't have smooth pasting at at this solution. I have smooth pasted for the monopoly position because then you have a single optimization. So now I've received on Sunday comments by referee. Usually you get surprises from referees and not most of the positive side, but this was an exception. And basically the referee report, I mean, in terms of comments and insights and length, and he or she argued that you can look for nonlinear strategies. You can look for nonlinear strategies, look at the left one, of course you can compute them, but the essence of the argument remains the same. This is would be the symmetric game, no matter what nonlinear strategies you choose, the symmetric game does not give a generic solution for the asymmetric game. Here, I tried to impose some continuity for the second player, but of course you see this continuity for the second player that I imposed still leads to a jump from the first player, but with the absurd result in this case that the first player, who cares more about global would emit more than the second player. But again, to cut a long story short, even if you're allowed for nonlinear feedback equilibria, and even if the true equilibrium of the scale is really nonlinear, you cannot avoid the jumps that will take place the moment the first player stops emitting. Now, I don't want to go into detail, but the point is, if I go to the full Doppler long model, I allow for depreciation, you still, once you have asymmetry, you get the possibility of a jump, even if the steady state solution of the game would allow an interior solution. Here is the steady state. Here you see both players in the dashed lines still in it. Nevertheless, the optimal equilibrium strategies are the bold ones, in blue. So depreciation, so ignoring depreciations simplifies my task, but it's not that true. So there are related to this. I don't know how much time. Okay. So this is one of the important points that for me made on Sunday is we wanted to have more discussion on the underlying game. While I thought the major message, and therefore it's very short, of the paper is that the symmetric game is not a generic representation. But if you, and I think this was true, apply to the Warner games, then it has an interesting implication because it gives some support to human interactions. Yeah. The second implication is, thank you for sending me the paper, is the presentation I did some time ago, is the Brexit game by Raoul Feichtinger and two others, because in this case, the Brexit is for sure, because if the player decides to go from the cooperative to the non-cooperative, from the cooperative to the non-cooperative solution, he knows that in the second stage, sometime he will get the monopoly position. And this will almost for sure deliver higher profit than staying in the corporation. Okay, then a remark about symmetry and games. If you have n-player games, yeah, this is Luca gave a presentation. I just referred to you in two examples. The following: if you have an n-player game, symmetric players, all of them, and even if you do the computation, the equilibrium is the only equilibrium is a symmetric one. Okay. So then you think you could simplify the solution of the n-value functions to two-value functions that you have player I and then player j as the representative competitor, and then you have player j, you all have to multiply these terms of v prime and so on by n minus 1. But the plain truth is, I don't maybe look at an answer, I think it's the answer to the Kant equation. The plain truth is, if you try to solve the simplified version for the two players, you do not get it. Okay? And then another issue is in higher order games, you can obtain multiple linear fields. But this is just a little. Okay, I come to the summary. As I said, I came to this story by Engelberg, and my original motivation, somehow I have returned here, is that this is somehow useless. But as admitted, if you can't use it. So this paper, this presentation expressed that the common assumption of symmetry used in differential game theory should be applied, at least in some cases, with caution. Yes, I repeat, there are many games where you can do this. No. So I show that this can be highly misleading, but in particular cases. This holds in particular. So the major takeaway, to repeat, is not so much the game of Dr. Law, although I think I will have to work on that. The major takeaway is that the symmetric game need not provide a generic representation of an economic situation. But of course, so extensions, easy to think is, one is already sketched, you could allow for propitiation, which is not true, as I showed. Then, topic from implications perspective is the application to justify unilateral action in global warming games, but this will become very complicated if you allow, for example, for n different players with different preferences. Similar result is for sure in this investment game that has been quoted by Wirl. There are further examples, and I think, for example, the Shadow Lake mode would be interesting because then we have multiple thresholds for each player. Of course, with multiple players, you lose some other nice properties of working with the face plane. Then this is now beyond my scope, is that the asymmetric game introduces jumps or discontinuous in the strategy. And this creates a problem on its own, and this is beyond this paper and beyond the capabilities of this author. But just to mention, Schumacher and Alterer, Schumacher and Wirl and somewhere else, and Darko and Gardner, of course, discussed and introduced the necessary mathematical methods and apply them to the essentially the same graduate comments that I have presented here, but both of these papers retain the assumptions. Thank you for your attention.
My work and for having always a keen interest for what I come up with. This paper of Mikko Jaakkola and myself is not solving all the problems that Luca and Franz have presented now, but I think we give the tools to for some work for the next 10 years at least. Okay, yeah, that works. Thank you. One thing I have to say as a disclaimer, Franz, we do have results on the asymmetric case. It is just that our application is a symmetric one because then we can draw things. Okay. I know you all know game theory, but just to be on the same page. The normal form of a game, so we've got n players. Players have a strategy set, they choose the strategy from the strategy set, they receive a payoff, and we write the payoff in such a way that we emphasize that the payoff to our strategy is computed by having the other strategy fixed. Then, given the choices of the other players, we can define a best response set. It's just a set of all strategies that are maximizing our payoff given what the other players are doing. And strategy profile is Nash if every strategy is in best response set to the other strategies. This is the same for all games. Okay. Now, we are looking at an infinite horizon differential game. And we have a very Well, we've got a fairly restricted class for which our results hold. The state is in a one-dimensional space. We've got a utility payoff which is decreasing in state, so we're thinking of, say, illusion games, but you could of course invert signs and have it increasing. And we've got strict convexity in the action variable. But as you see, we allow that everything is different for every single player. Now, in differential games, there are basically three large classes of strategies. There's the open loop strategies, where the strategies are just functions in time. There's closed loop strategies, where there are functions in time and space. And in the infinite horizon context, there are the feedback strategies, where the actions are actually functions of the state only. Now, we are focusing only on feedback strategies. We've got system dynamics, we've got very simple system dynamics. It's the change in the state is the sum of the action of the players and some possibly non-linear term. This is our context. Now, there are two big puzzles here, and I probably have missed half of the literature, but these I think are important papers. The first question is, how many of these feedback Nash equilibria are there actually? We've just seen, Luca reminded us that there are in the Schwartz, first model, there are infinitely many. Now this is one model which is not in our context because they've got a payoff that is first increasing and then decreasing in the state. Von Kuch and Zero have a pollution problem we're going to use as our example, where this works. Tsutsui and Mino talked about, well, there can be infinitely many of these strategies, but then later Colin Rowe pointed out, well, there's a problem, because these Tsutsui mini strategies are defined only on parts of the state space. But a strategy needs to be defined globally, because, why? Well, one of the players, by doing something non-equilibrium, could take out the play out of the region where the strategy is defined and put it, force it into the undefined region, and then you don't know what you're playing. Vienna, what's just mentioned, has put some of these points again in sharp relief. The second question we also address is that there are games where there are no continuous feedback Nash equilibria at all. What do you do then? The Sherman Lake game is one of those where there are no globally defined continuous feedback Nash equilibria, so you have to look at equilibria with terms. So this is what we do. We try to find in our context all Nash equilibria, well, not all, with finitely many terms, but I'm prepared to say that this is the most important class of Nash equilibria we want to know. Okay, so this is my example, the transboundary pollution problem. I think it goes back to reconstruction IIASA. It's the same model as in the Dockman and Van Long paper. You've got emissions, which say they come from a feedback strategy. We allow them only to be in a compact interval. These emissions affect the pollution stock, say atmospheric CO2. This is very simple linear evolution equation, and there are payoffs. And now these are the game payoffs, and these are the payoffs of a single player of an optimization problem. The single player is looking at that problem while he was thinking that if all the other players have their actions fixed. There are these quadratic benefits from industrial pollutions, first increasing and then later on decreasing. If you overproduce, it's no use. And there are pollution costs. And as a discount factor, and you'll notice here that this payoff functional is the same for all players. So we are indeed looking at a symmetric case. Now, we can define the value function of the optimization problem of the single player. So it's just the biggest payoff that can be achieved, and that is achieved by some kind of action schedule over time. Okay. We want to find a feedback strategy space such that the game is strategically complete. This is a notion we introduced. So what do you mean by that? First of all, in the feedback, the strategy space should be such that whenever the other players take their strategies in their space, then the best response should exist in the space of the ith player. The best response should be there, but the completeness part is that the best response should generate an action schedule that is also the optimal control of the player. Yeah? So you can imagine that if I give you just, say, a strategy space of 3 strategies only, there will be one of them that is optimal, but it might not be coinciding with the optimal control. Now, for instance, if you think about it, if you think in the linear quadratic context, the space of linear strategies is strategically complete, because the best reply to a linear strategy will always be a linear strategy. But if you look at a broader strategy space, then you can pose the question again, what do I need for strategic completeness? Okay, now the first thing you want to try is just sufficiently smooth strategies. But if I allow them, these strategy spaces are not strategically complete, and I can show that in the case of the transparent evolution problem. If I choose, say, for 2 players, if I choose for the second player the nonlinearity of the shallow deck, because I know that in the shallow deck the best response will have a jump, so it will be a strategy with a jump. So that means that I'm already out of my strategy space, because I need to admit something that is not even continuous. Okay, I can try to get away with having piecewise smooth strategies. Okay, but then I've got the next problem, because in my dynamic equation, I have now here a term that is discontinuous, and that means I've got jumps on the right-hand side. And that means that I don't have Lipschitz continuity again, and then going back to my course on differential equations, if my right-hand side is not Lipschitz continuous, I can't guarantee existence and uniqueness of solutions. But the uniqueness part is the problem. What can we do there? Well, you go to the Filipov and say you can replace the right-hand side by actually set value functions, just interpolating over these gaps. And then I can replace these dynamics by a differential inclusion. Basically, I allow the solution that I can be 0 there. And then solutions exist, but unfortunately they're not unique anymore, but at least we can talk about solution paths. Is this solving my problem? Unfortunately not. So next problem is, well, if you think about, if I'm giving the strategies of another player, how do I compute my strategy? Well, basically what you do, you write down the state co-state system, and in an infinite horizon problem, the best reply is constructed by looking for the stable manifold of a certain sample, several samples. Now,
that's for open loop. Here,
I'm only talking about feedback.
okay, so why do you use this state approach, which
because this is the way I can construct even a strategy. First, because I'm only looking at the best reply problem. The best reply problem is the optimal control problem. Yeah. Okay, so how do I construct my best reply? I solve this optimal control problem, and the best reply is then the stable manifold of a sample. Now, if the right-hand side, if my vector field is, in this case, ck minus 1, the stable manifold will be ck minus 1. It will be 1 order of differentiability lower than what I started out with. So CK strategy spaces are also not strategically complete. What can I do to get around that? Well, go to piecewise real analytic strategies. Now remember, the function is real analytic if at every point I can develop it in a conversion power series with a positive convergence radius. And of course I have to do piecewise analytics because I need to include jumps. And then I additionally need a limit condition at the jump points. Is this solving my problem? Well, it's almost solving the problem. But mostly. This is our first result. There is a Noah dense and Schei set in these strategy spaces, such that if I stay away from this Schei set, I'll talk about Schei in a second, then there's exactly one best response, which is also in the strategy space. Have a set that has measure 0 in this big strategy space. Unfortunately, measures can't be defined for function spaces, but what I can do, I can move a finite dimensional manifold around and look at the intersection of that manifold with the set and say, okay, this intersection should always have measure 0. It's a bit more complicated than that, but this is more or less nice. Okay, so almost always I have a best response. That is already saying something, but I can actually characterize it. I have got a theorem, something is the best response if and only if, so necessary and sufficient conditions, if 4 things hold. Well, the first one is the Hamilton-Jacobi equation, which is basically saying that my action is maximizing the Hamiltonian, what you would expect. The second is, this is typical for these kind of problems, for these kind of solution problems, the value function should be decreasing. There are some natural conditions which I don't want to write down at the value discontinuities, but if you see them, you say, I hope you say that they're natural. Most important, if I've got a jump point, and if this is a push-push steady state, and what do I mean by push-push steady state? I mean that the dynamics will come in from one side and they will also come in from the other side. And you would, well, typically these are points where you've got these scattering solutions. You can't stay still at the point, but you can jump around. Then the value function of the best reply is differentiable at that point. So that means that even if there's a jump, my best reply will have a differentiable value function, which means that the best reply action will be continuous. And then you can see that if I extend that to Nash equilibrium, then this must hold for every strategy, which means that there can't be push-push steady states in equilibrium. And that gives us a very strong handle to exclude cases. Now, this is only a theorem about the best reply. We can now write down a theorem that characterizes all symmetric Nash equilibria, well, of where the value is continuous, with finitely many jumps, and there are only 3 conditions. This function B is nothing else than the Hamilton function of the problem, but expressed in actions, because in the interior we have a one-to-one relationship between co-states and actions. The first condition is that the graph will find some kind of allowed region, I'm going to show in a second. The second one is that it satisfies a certain differential equation, it's basically the Tsutsui-Mino differential equation. And the third one is, of course, that the Hamilton is continuous over jumps, because otherwise we won't have a continuous value. Here is the region. So these 2 triangles are part of the allowed region, and the allowed region has a horn in this direction, and it has a horn in this direction. Here, in the middle, you see the linear strategy. And here, if I'm looking at this G function, at the Hamilton function, it will be minimal at this dotted line. And actually, this is the isotime line of the state-co-state equation, so this is the singularity of the state-co-state equation. Now, This means that if I'm having the state constant and I'm going down, then the value of my Hamilton function, and so my value, will be decreasing until I hit this dotted line, and then it will be increasing if I go up again. Now notice this. Here we've got the linear strategy. If I go below the linear strategy, I would have lower values, but then I'm always in the forbidden region. Here, I get lower values if I go up, but that will be in the forbidden region. Which means that the linear Nash equilibrium is the one with the lowest payoffs of all other possible Nash equilibrium. Here the intersect, this is the line of the steady state, so here we get a steady state of the linear equilibrium. Now, what kind of nonlinear equilibria could we have? Well, here are two of them. Which is going up here and then takes a jump, but it's a continuous value jump. Then it goes up again, takes another jump, and then it continues along the linear equilibrium. Here's one with a couple of jumps. And you can see in this way you can construct infinitely many equilibria that will have more and more jumps. Now, I tried to compute the values of these Nash equilibria. We did. Thank you. We made a calibration on a CO2 pollution problem. This is only the relative values. We took at the baseline the case that people that we've got 5 players here, that the players do not care about pollution at all, so they don't consider a cost in the dynamic function. The 100% case is the cooperative case, so that all players work together. Well, we've got here the linear Nash equilibrium, which is already getting about 1/2 of the possible gains. Here is, of course, 100% the cooperative case, and here's the best Nash equilibrium for this for a certain initial stop. And you see it is between 80 and 100% of the cooperative line. So we can, in certain cases, actually get at a cooperative value with a Nash equilibrium. Now this addresses a point of Luca's. We've got now so many Nash equilibria. What to do with them? Well, maybe we should think differently about these games. We always were very much interested in the prison dilemma. Why? Well, 2 things. First of all, it has such a wonderful story. We're doomed because we're greedy. And there's only one outcome. But apparently there are many outcomes. Some are better than others, but we need to coordinate. As Luca mentioned. But this is a good thing, because it is highly unlikely that there's only one way of proceeding. But coordination is key in many economic activities. And in many other activities, we don't worry about many Nash equilibria. If I and Franz want to meet somewhere in Vienna, there is an infinity of meeting places. Every meeting place is a Nash equilibrium. If we don't make an appointment, well, we won't meet. But if we make an appointment, it's very simple, we're going to meet, and neither of us have an incentive not to show up. So these Nash equilibria can support agreements, international agreements. And at the moment we are pointing out the range of Nash equilibria, our work as economists is done, and we can hand it over to politicians, because they have to actually do the coordination, and that is pretty hard work, isn't it? Okay, so we have all the piecewise real analytic Nash equilibria. Some are very good. Also, I mean, of course, they require pretty drastic policies, because this is an output reduction from, well, basically business as usual where we are, to something very, very small. In more complicated, more realistic models, this will look differently. But I assume, I conjecture that these kind of radical solutions will persist also there. And communication and negotiations are necessary tools to communicate. Thank you very much.
Equilibria always fulfill only some necessary conditions for Nash.
No, we use viscosity theory, and there's a special. It doesn't have to be continuous for that. There's an extension for discontinuous variables.
Further questions?
For me, the fascinating presentation here.
I'll send you the
Fascinating presentations here. We did some little work on Nash equilibria and using algorithm of an NPC. And Lars already, Wirl, who invented this, warned us, you won't find much stability if you have two payoff functions which are asymmetric. And so this was a general remark, and you were puzzled about this, but we have no proof of this. Why is it? And a student of this has a proof there. Why that's difficult. To Luca, I was wondering. You are using basically the very traditional theory of excess demand function, where you have one payoff function, and the control variable is price. So what about when you what?
The control is one
Yes, but it's the same. It's the same in the payoff function.
Okay.
Yeah, and that's what Franz was trying to move away. And so there is a tradition in industrial organization having this game. Ken Judd and others who use basically two different payoff functions. One firm is doing the pricing, and the other firm is adjusting in quantitative terms. Mm-hmm. So you would have basically a quantitative decision in the payoff function and the price decision by the other player. And that is a little bit more complicated and probably gives rise to, we have solved this numerically,
yes.
but it's, we have no analytical results on this. So
Yes, not in differential games. I mean, I know many asymmetric games of that type, where when I may be a price setter and you are
exactly, you are entering
in
into
some
a
games
quantitative
it's okay, it's a little more elaborate, but it's not scary, okay? In this case, is absolutely doable in linear strategies because of the asymmetry of the two initial strategies. So if I control a price and there is product differentiation and you are controlling a quantity, you have two states and two controls because we need product differentiation in one state. Okay. And that makes the differential game immediately totally asymmetric. And then forget about the characterization of the control.
Okay, nice, yeah.
As is also in the case of multiple states, because we are short of equations in that case. We need 50% more, and we have not. So, because we have to deal with the second partial derivatives, and these become.
Good. Very
So in a sense, the problem with nonlinear strategies can be also seen as a secondary one because all we do is to generate the continuum of nonlinear strategies in presence of symmetric games with one state, which is a very, very small subset of everything we would have in mind and we would like to solve. So it's not a trap.
Okay, thanks.
If I can put a footnote to both your talk and your remark, what is sorely needed is a theory about how differential games will be played, because this is only the equilibrium theory. But the question is, how do we get at equilibrium? Now, in ordinary games, we've got something like evolutionary game theory. I don't know of anything that is remotely convincing in case of differential games. But this would be very interesting, and that kind of refinement would then talk about stability as well.
Yeah.
Like your last statement that the game theorists can somehow identify all possible Nash equilibria and then somehow coordination is needed to make. But what in the case if the coordination fails and one player plays that and the other one that? So both players are not binding to this coordination then. So what happens then? I mean, you have then just a dynamic system, and both players or all players do not get to some best response. So how to deal with that question?
Well,
with the coordination thing.
If I and Franz arrange to meet at the Carter, and I'm going to the Stephansdom and he's going to the Carter, yes, then coordination fails, and then we've got a problem. But I think your question is again a question after how are these games played? And what happens if there's no coordination? So how do we adapt strategies? Now, one way of modeling how a game is played is that you look at the best response dynamics. I announce something, you pick your best response, I take my best response, etc. This strategic completeness allows that we can actually do this best response dynamics, and well, unless we're very unlucky and start in this exceptional sense, but I can characterize that it will converge somewhere. And the question is, how are we going to implement that in a practical situation? I don't know. I mean, the main point I want to make here is that we've got now a whole range of open problems. The asymmetric equilibria Franz was talking about, it's an entirely open thing. Okay, Dumas and we have worked a little bit about it, but there's still a lot to be done. The multiplicity of equilibria, what to do with that exactly, and how to think about it as a regulator. At least we've got now the tools to compute them in many cases, and we can start to think about that.
If I may comment, say, if countries or governments coordinate openly in sunlight, they are welcome. So in that case, cooperation to generate, say, energy efficiency, because we are talking about environmental problems, as well. When it comes to France selling consumption goods with no hint about and you realize that I'm not there, and this is a strategic mistake. If we do that, and we never ever say approach, say if this big fact the behavior of the hotel, the public authority opens the best coverage. It depends on the context.
Do we have further comments, questions? Yes.
There is a paper by Alma agreeing with this integration. And there's a deep interest in the real common knowledge. What's the common knowledge what the from dynamic is. So I think this might be relevant for the program discussion. How they
That is another one of the many extensions we have to do. But thank you.
Okay, if we don't have any other fun.
I have a small question. So what should we do now? I mean, because we suppose we want to write a paper and use the usual approach, like to swim and move. We actually have a high risk to be rejected by drawers. So how could we actually reduce this risk?
I cannot say that. I think the first thing is there games, for example, the game that I've used is if you have the utility hyperbolic absolute disconversion, you can show there's no singular equilibrium, there are only infinite. So in some sense, they are not in the general context. Not right, because the games were only infinite. Now, coming back to my chart, is where we have a symmetric game. We have delta is equal to 0, so but now the exit in finite time, infinite time, smooth pace in cycle. Yeah? But now we stop in finite time. which is not defined by the nonlinear strategy. Das heißt, it would give a non-dynamic, nonlinear solution. So, my very cautious answer is, taking Bernhard's critique, right? Emphasizing it's not Europe. There are some games where this approach is inappropriate. But there are definitely other examples where you cannot get rid of the mean people.
I think that checking the sufficient condition, if you have a sufficient condition, of course, the judges cannot say that the referee will just accept it or let it off, but then it cannot be said that it is not equilibrium because it is. So you have a sufficient condition. However, you obtain the results.
It's an if condition, so it is sufficient.
Okay. If there are no further comments, then I think we can thank all.